Here we go, Beast! Woo! All right, one! Yes, sir!
I tell you what, that's dedication. That's what I'm talking about. Hope you're having a fantastic night tonight. We're about ready to get real, team. About ready to get ready for, first big test. This is our midterm. Hey, I know there's a lot of questions. I've got stuff on my phone from different classes. I've got resources on my left, resources on my right. Man, I'm ready to get it rolling. If you have questions, I've already gotten some texts in. Feel free to text in there, and we'll get it rocking and rolling. But I don't want to waste too much time. I want to get right straight into it because I know there's a lot of stuff that we want to go over. So let's get started, and let's rock and roll, okay? The first thing that I got texted in here that even before anything, anyone came in, Morgan, thanks for sending this in here. It is marginal distribution. And as you throw things out there, just for example's sake, I'm going to end up kind of going back to some of the questions from the previous chapters. And this was in chapter 1, if you remember this marginal distribution. If you remember, there was kind of a question on the quiz, I believe. Our first quiz, I believe it's the first quiz there. And I'm getting to it. Yep, sure is. Let's talk about this here. We have, when we talk about this specific, hold on just a second. Hoping this will work here. Trying to get the pad to work here. Sorry about that. We're going to get this rolling. Remember with marginal and conditional distribution, conditional means we put a condition on it, right? Marginal means we're pretty much filling in what was given to us, right? What was given to us there. And this is not working. Let's see if we can go on this other side here. And I think they switched some stuff up with my Mac, and the pad does not work. Okay, so this is where we end up going out there. Wow. Okay, sorry about that. We're gonna make do with what we've got. Okay, so what they have is this. We have male and female here. Okay, within our section. So we got male. Sorry. And female, okay? And over here on this side, we got our Democrats and we got our Republicans, if you remember this here, right? And when we looked at this, if you remember, there was, if you can imagine this here, and I'll even try to draw this in by hand, we had this like chart, right? And remember with marginal distribution, this is just a basic example, and they had their others, right? There's actually another column that was others here. And what they said was this was 200, right? And the Republicans were 500, okay? And the Democrats were 300, okay? So we got that. So the question with this one was, if you could remember, the question was trying to assess what the distributions were. And they kind of gave that this was 600, my fault. And they gave that this one was 300. Right? And the others were 100, right? And really, to be honest, you could total this up, right? So as you kind of came this way, you could total up and say, okay, this is 900, right? There, and then this is 800, right? These could be like your totals, right? And so on and so forth, okay? So when we talk about marginal distribution, if you remember, we're trying to find a percent, but it doesn't have any specific condition on it, okay? So, and again, I guess with the totals, I guess that would help us out because as I come over here, right, if I were to look at the total of 900, and I were to write this in, and I were to look at 800, I were to write that in, and I were to write 300 right here, right, so on and so forth, and I could come all the way down here, right, here and here, what we could say is what percentage were male, right? So what we could do is because of the total being 2,000, right? Marginal distribution is just simply telling me what a specific value is percent-wise. So if this was 1,000 right here, I could go down and say, okay, what percentage are male? We know that the marginal distribution of that would be 1,000 over 2,000. And that would be a total percent. That'd be 50%, right? Okay. Now with the females, we know that this would be 1,000 on this side. Okay. And just like before, this would be 50% on this side, okay? 1,000 over 2,000. Now over here, we would do 900 over 2,000, 800 over 2,000, and 300 over 2,000 to get what those marginal distributions are. But remember when we talk about conditional is exactly how it sounds, puts a condition on the specific value, right? So if I were to say what percentage of Democrats are male, okay? What percentage of Democrats are male? What I would be saying is the percentage of Democrats, again, we're focused on what? We're focused on the Democrat side, right? So what percentage of Democrats are male? We're saying that Democrats is the given. What percentage of the total would be male? So we take 300 divided by 900, and we would find that 33.3% would be the percentage of the conditional distribution of males, or of the percentage of males that were Democrats, okay? Now, what if I switch that around? What if I said, what percentage of males are Democrats, okay? So what I'm saying now is it sounds very similar, but I'm backing that up. I'm kind of doing it just a little different. I'm saying out of all of my males, what percentage of my males are Democrats? So 300 over 1,000. And in this case, I back up real quick. I want to make sure. If I did 300 over 1,000, that would be 30, right? Whereas the other one would be 33.3%, okay? So the percentage of males that were Democrats is different than the percentage of Democrats that were males. And so you have to kind of, in that conditional distribution, we're putting a condition on it to be able to solve and figure that out there, okay? Hey, Morgan, if that didn't help you, please let me know on that. That was a really good question, and I appreciate you for addressing that there. The next question comes from V a little bit. V says, can you do an example problem of residual plot problem? Yeah, absolutely. So remember with the residual plot, it's important to note that a residual plot is something that the x stays the same. So our explanatory variable within our correlation, where the x is the explanatory, the y is the response, right? That's always the case. We remember that the y-axis is our residual. We also remember that when we do a residual, or when we focus on our residuals, in order to be a good predictor of a least square regression line being used, to have proper evidence, we would have to have a random, right? Remember this? This would have to be random, right? Not that line, sorry. But this would have to be random. If it's just completely scattered, not random, on this residual plot, we can say that we have enough evidence to say that a least squared regression line would be a good way to determine the correlation here. But let's say for some reason, fortunately, it wasn't the case, right? Let's say that there was some sort of pattern to this. Many times this pattern will be, it'll be something like this. Maybe it just kind of follows a specific pattern here, where you could kind of see that it will follow maybe a parabola or a parabolic shape, or let's say it follows maybe it just kind of goes up, or that's all on one side. In that instance, we'd say that a residual plot would not be effective in determining, or I'm sorry, back up. We would say that there's not enough evidence to say that a least squared regression line would be the best case. We can't say that, oh no, there's no least squared regression line used. All we say is that there's not enough evidence to say that a least squared regression line would be the best fit line there, okay? All right, let's talk also about a matched pairs design. To do this, I'm gonna do this. I'm gonna have, let's say we rank the GPAs of students within our AP stats. Let's say we have 10 students that we have, okay? So we'll say, we'll do this, okay? Just trying to throw some down there. 3, 6, 7, 8. Let's go. All right, 2.1. Okay, so let's say as I look at this, okay, these are some of the higher GPAs in stats, right? A matched pairs design. Well, let's talk actually a couple things, okay? Let's talk about a block, okay? First off, let's say that we have 10 students, okay? And as we have 10 students, we want to place a block on this, okay? The block allows me to put two types of students here. Maybe within my AP stats class, there are, I don't know, let's say that the block is those that have, I don't know, I'm trying to think of something that would be those that have had an AP class before in math. So AP in math, right? And let's say that we have our, actually, let's do this. Since we already have GPA, we could do this a bunch of different ways. Let's just do GPA. So let's say this right here is another 4.0, okay, just to make it easy. So we'll say our 4.0 students will be at our first block, and our 3.9 or lower would be my second block. And let's say within this block, we were trying to compare the effects of collaborative learning or individual learning within AP stats. A block would say, okay, I'm going to randomly assign, sorry, no, it's all over the place. I'm going to randomly assign, that's what RA means, randomly assign two treatments. One treatment will have collaborative learning, the other, individual learning, okay? And again, this would provide more, I need to provide more information, but the pad just went out there. And so we're just going to do this here. And then remember, we compare only in the blocked phases, right? We only compare here. So we have our block, we have a random assignment, we have the two treatments. Treatment 1 was the collaborative learning. Treatment 2 is the individual learning. We compare the results at the end on a test or on an assignment or whatever. And then at the end, we'd be good to go, okay? Now let's say we stopped with a block design and we did a matched pairs design. What we're trying to do in a matched pairs is we're trying to have two different groups to receive two different types of treatment. Treatment 1 would be here. Treatment 2 would be on this side, okay? The difference with this one is the fact that we want to have equal groups to be able to see if the two compare. So because of that, we've done GPA. So we've ranked them in order from highest to lowest. And we said that, okay, in a matched pairs design, we're going to put the highest one in treatment 1. We're then going to put the next highest in treatment 2. 4.0, treatment 1. The next 4.0 in treatment 2. So as you go here, right here, this one 3.7 would go here. This is called a matched pairs design. Because what you're trying to do is trying to compare apples to apples. And in doing that, we're just trying to go every other one after we have ranked the individuals, where you have 5 in treatment 1 and you have 5 in treatment 2. And then you initiate what the experiment would be there. That's a matched pairs, okay? But yeah, I hope that helped you there. Casey, the least squared regression problems like the ones with the green dot in the escape room today. Oh gosh, are you ready? It's a lot with that one, isn't there? Okay, let's do a least squared regression problem. Let me see if I've got, is there one that actually does that within our problems here? Let's see. Oh, okay, here we are. Let me see here. Oh, yeah. Okay. Trying to see. I'm looking right here. I'm making sure. Okay, perfect. Let's go to Casey. If you need more than this, please tell me. I'm going to look at the problem I'm going to look at is 1.17. It's the very last problem on here. In fact, I think I've got it. It's actually right here. Yeah. Look at this one. If this does not suffice for that, please let me know, okay? Please let me know there. All right, so let's talk about this. Now, because of the fact that, actually, let's do this. I'm going to try to type this bad boy. Okay. Oh, yeah. Here we go. Man, we're dedicated right here. We're like Matthew Wong, Beyonce 12.0 right now. All right, here we go. Let's talk about A. It says, describe the relationship between shelf length and sales. Okay, so first off, Remember, this is not SOX. This is DOFS, okay? The reason why is DOFS is related with correlation, right? So that's very important. So let's talk about what the, and again, there's no free response on this, but maybe we could, as we go through this, there's going to be a lot of things that we can take from this here, okay? So let's say DOFS is correlation. Let's say that within this, the D, the direction, the outliers, the form, and the strength. So I'm going to say, and then I would put that in context. So right now we're talking about shelf space with the sales in dollars, okay? So as shelf space increases, the sales in dollars increases, okay? So when looking at the correlation between shelf space and sales in dollars, we find the correlation is a strong, positive, linear relationship. What did I just hit there? I hit strong positive, linear. Positive is direction. I haven't hit outliers. Form is linear. S is strength. I hit all three of those right there, okay? So I, again, didn't have to say too much. Strong, positive, linear relationship with no perceived outliers. I don't know if I could have written that better. That's pretty good. So when looking at the correlation between shelf space and sales in dollars, we find the correlation is a strong, positive, linear relationship with no perceived outliers. That right there is money, okay? Also, if you check me on the answer sheet as I go through, I have it here, but I'm going to try to do a lot of these without. But if there's something like a tweak or something that they have, let me know and we can talk through that, okay? Write the equation of the least squared regression line. Well, we know that as we look down here, we've got the shelf length, which would be our x, right? So this would go with it's our coefficient. We put that with x, right? And the this right here would be our value that would be by itself, right? So the y-intercept. So we would say, to be honest, I like to put this in context a little bit. So my y would be sales in dollars equals with a hat on it, okay? It would have a hat on it because it's projected. It's not absolute. Equals 152.680, and again, context, so we'll put shelf length, okay? And then plus 317.94. This is the y-intercept, right? Remember, the y-intercept states, this is huge here for interpreting this, when the shelf length is 0, or we have zero feet in shelf length, it is perceived that we will have approximately $317.94, and I think this is per month. That might be something to include on top there that I was when we talk about sales, but that's kind of what you would put there. The actual slope here would mean this. Remember, this is over 1, right? So we would say that as we rise 152.680, we run 1, okay? So as the shelf length, because the 1's on the bottom, right? Okay, it's rise, which is y, over run, which is x. So as the shelf length increases by 1 foot, it is perceived that the predicted sales in dollars would increase by $152.680. Okay, so that would be how you would write that in, like if I asked you about that there. Okay. C, if the store manager were to decide to allocate 5 linear feet of shelf space to the store's brand of men's grooming, what is the best estimate of the weekly sales? Well, what we could do is just plug this in, right? So when we plug in 5 in for the shelf length, right, we can say 152.680 times 5. And then I'm going to add 317.94. The predicted value would be, and this is what I have, 1,081.34. $1,081.34, and that's how we would write it. And we would say it would be like y hat, right? The hat should be here. Okay, hat should be here and here because it's projected. Okay, it's not actual, right? It's not the actual value, but it is predicted. It might be a pretty good predictor there. Okay. All right, let's keep going. Sorry, I'm gonna move this part over to this side. There we go. All right, let's look at D now. D says, interpret the sale or interpret the value of S, okay? Remember, what is the average of the residuals? The average of the residuals states that the average will always be 0, right? Because you always will have some that are positive and some that are negative or pretty doggone close to 0. So when we identify or interpret the value of S, S is the standard deviation, which is the standard deviation of the average error each value is from the actual least squared regression line. So S, or we'll say S of X, okay, is the average distance each value is from the least squared regression line, okay? Now, in context, we could say, I'm trying to think, S of X is the average. You could say average error. I don't know if that really has context. Maybe if it does, if I taught that, let me know. But really the big deal, especially for the multiple choice, is determining S of X is the average distance each value is from the least squared regression line. You could also say, if you really want to be politically correct, you could say something about average error or average residual is really what it is, right? And you could do that and go from there, okay? All right, let's keep going. E, what does E say? Identify and interpret the coefficient of determination. Okay, the coefficient of determination is R squared. Now, here's a really big thing, okay? This is something that you just got to kind of know, okay? Remember that R is the strength whereby the values or the dots scatter plot are tightly bound together, right? The closer they are together to forming that line, especially in the positive direction, the closer it is to 1. And if it was in the negative direction, it would be closer to -1. Remember, if this thing is scattered, this is just a reminder, okay? If this thing was all scattered, this thing would be headed towards an R. An R equals 0 means that it is completely scattered, right? R equals 1 means that it's a perfect, like it would be a perfect line, right? Perfect line, perfect least squared regression line, all would fall there. And a -1 would just mean it would go in the negative direction, okay? So with that in mind, we have to interpret the coefficient of determination. Coach Jay hopes that he can remember this. If we remember, this stands for, and this is at R squared, 98.2%. Remember, it's the percent of variation of Y on the least squared regression line as it relates to X. This is the perfect definition, okay? Now, I have to insert all of the information, but R squared is just saying how, basically, what percentage of values falls within the variation of the least squared regression line, right? The more spread out they are, it makes sense that the R would end up being closer to 0, which would also decrease R squared, right? So when we say this, again, huge here, we would say that 98.2%, I already said percent, so we don't have to put it, of the variation of, and let's put the context here, of the sales in dollars is related to the least squared regression line as it relates to shelf length, okay? That's R squared. That definition, as I've looked at it there, that definition, they expect you to kind of know that kind of that format there. So that would be the coefficient of determination, okay? And F says the store manager questions the intercept of the regression line. Am I supposed to believe that this analysis tells me that I can sell these products with no shelf space? How do you answer her? Well, remember that when we talk about something that is outside of our this is our least squared regression line, somewhere through here, right? Wow, that is really fun. There we go. Somewhere through here, right? And so because of this, this goes all the way to, I think it's 3, right? Something that's on the outside of 1 would be like way down, or I'm sorry, 0 would be way down here, okay? So when we talk about the slope, he's saying that when I have 0 shelf length, or 1 really, oh, I'm sorry, not that one, my fault. I was looking at slope. When I have 0 shelf space right here, right, the y-intercept is $317.94. And so what he's saying is zero shelf length means that I have this. Well, you would say that because this value is way outside of the actual scatter plot, this is called extrapolation, right? Remember this word? Extrapolation means that you're trying to use the scatter plot to determine something that's outside of my range. And so because of that, you could defend this and say, hold on now, that doesn't mean that this doesn't necessarily mean that you could make $317 without any shelf space. But what it does mean is that the dot way out here is outside of my range of my current scatter plot. Therefore, we have extrapolation, and we can't properly determine what the amount you would have when you have zero, like zero shelf space or zero shelf feet there. Okay. Hopefully that made sense what I was saying there. Casey, hopefully that made sense. And as we go through, if you do have more questions, keep them coming. Okay. All right, Matthew coming in hot. I see in there. Love it right now. Love it. I have 5 viewers here. I know that it's just going to continue, so continue to go from there, okay? Good. I got that one. Oh, I'm sorry. Morgan, I'm sorry. I didn't see the variance versus variability, okay? All right, so variance is something that is important to note, right? Remember variance, the formula for variance, and see if I can remember this here, is the sum of all the values of x, right? Right here, subtracted from its mean. Sorry, this shouldn't be here. Okay, all the values of x subtracted from its mean squared, right? Divided by n minus 1, right? And we take the square root of it. This right here is the definition of what a standard deviation is, right? A variance is the same thing as a standard deviation. The only thing about a variance you need to know is it's the standard deviation squared. So we actually don't even have like a symbol for variance. We're just going to say variance. So variance is the standard deviation squared. Also, the variance square rooted gets me back to the standard deviation. So if you were to eliminate this square root, that would be variance. Now, we hardly use it, right? We don't really use that. We use more standard deviation when discussing spread. We also use IQR or range, depending upon if it's skewed data or if it's symmetric, right? So that would be what we're talking about. However, when we go to variability, variability is the spreading out of data. So if I say one piece of data is more variable, has a higher variability than another one, it's in that moment where we say that the higher variability is that the values vary. They spread out a lot larger than other ones that have a smaller variability that's there, okay? All right. Oh, man, we got tons of them. I love it. We did the residual plot. We did that. We did Casey's. Tony's coming in. Okay. Review using the calculator to find various aspects of a normal distribution. Okay. Here's the thing, okay? I'm going to be really real with you right now. I'm telling you, because you're watching this right now, this is huge, okay? I'm going to go to my calculator. I'm going to show you how it's done, and then we're going to go from there, okay? So look at me. I'm telling you, team, we got to focus on normal distribution. I do. I'll even tell you. I'll flat tell you right now how many, because I was counting today, and I found that there were a ton of them that had not variability. I'm sorry, that have normal distribution on it. So we want to make sure that we hit that really, really hard, okay? So I'm counting them out now. You ready? I see 1. No z-score. That's a big one too. We can hit z-score here in a bit. I see 2. I see 3. I see 4. I see 4 of them right there. Got me? That's quite a bit. That's a big chunk of it now, okay? Big chunk of it. Looking here. I'm telling you right now, look at, I'm sorry. Take a look at that one I was talking about, Democrats, Republicans. That's a good one too. I'm giving you some help here, giving you some help. I saw 4 normal distribution ones, and I might have missed one. In fact, I think I see another one. Yeah, I have 5 of them, okay? 5 normal distribution type problems, z-scores included, okay? So it's a big topic. Big topic, not just here, but also on the test as well. So let's get it rolling, okay? Because let's do that one. Let's do a couple of those. One thing I do want to recognize before we go any further is recognizing how to do some of the stuff on the calculator with the least squared regression line. I can't tell you whether that's on there. I'm telling you a lot with the normal distribution because you are on here, okay? And I appreciate you for being on here. I really do. You could be doing a lot of other things, and I appreciate that. Let's go to stat edit. Now for me, I'm just going to put in these random pieces of data. This is from our breakout room where the list 1 and list 2 is given. Let me just remind you how to do a dot or scatter plot, okay? So if I put this in L1, L2, this is my explanatory, this is my response, right? The explanatory explains the response, right? And these are the actual values, so on and so forth. Okay, so when I go to second y equals, I want to make sure, I'm going to press enter, make sure that this is on, and then make sure I've got a scatter plot. This is L1, the X list, explanatory, Y list is response. When I go to graph, okay, now hold up just for a second. I think I have this one on. I don't want to take this one off, so not to confuse you. Okay, so yeah, so I've got my this here. If you don't see that, remember we can go to zoom stat, okay, zoom stat. And that fits it in pretty nicely for us, right there. Now, what if I took that and I said, okay, I see that you got this least squared regression line right here, or I'm sorry, the scatter plot. I want a least squared regression line. What would that be? Well, that's a great question. And so right now, I want you to yell out in your house right now. Don't care what people think. Where would you go to be able to get to that? Where would you go? Well, let's go back to stat. And I heard you, okay? I know it feels like Dora the Explorer a little bit. By the way, shout out to Sweden followers. Just throwing that out there, okay? And the dedication of Matthew, if I haven't said that. Go to linear regression now, AX plus B. We want to make sure X1, or the X list is L1 and L2 is Y list. We'll go down to calculate. Calculate that there. And hopefully you see your R squared, so your coefficient, right? I'm sorry, coefficient. R is, dadgummit, I'm losing my mind. Correlation coefficient, right? And this is the correlation of determination, right? This came to me. So the R would be there. And then remember, R squared is the percent of variation of Y related to the least squared regression line as it relates to X, right? So go back and look at that. But that's how I would get this information for my Y hat equals our slope X plus our Y-intercept, okay? How would I go to find my residuals? Well, if I go back to stat and edit, I can go back to L3, go to the top, and you're going to go to second stat, which will go to our list. Go to 7, which is my residual, press enter. And this right here would be the residuals of L1 and L2 of that least squared regression line, right? That is here. So just a heads up on that, how to find that residual that's there. Okay, that's a big deal too. Make sure you know how to find that residual as well. Least squared regression line, I can't think of anything else that we could possibly use. I'm trying to see. Okay. Nope, all is well. Okay. We're going to kill that, and let's bring up our normal distribution stuff now, and let's start from the beginning. Let's try to hit some of these distributions here, okay? The normal distributions, I'm sorry. Okay, so we got there, no, not one there. I'm just gonna go through. Okay, yeah, this is a good one. I'm just reading to see what we can go over. Okay, let's go over these two, okay? Good ones. Let's go over 1.2 and 1.3. Okay, always, always, always when I come to these, I always draw something, okay? So when I see a normal distribution, we're gonna draw a normal a normal curve, right? Remember, this is a density curve because the area underneath it is 1. Remember, we talk about it like percentile, right? We always talk to the left of that line. That's very important. So if I look at this and I see that the mean is 38, okay, I'm going to put 38 here. And I see that the standard deviation, or we're trying to find the standard deviation. Okay, that's interesting. It says a child is 40 inches tall, okay? All right, so I know he's 40 inches tall. Okay, so I know if he's 40 inches tall, I'm going to go right here, okay? 40 inches tall, and I'm going to go on this side. So I'm going to highlight everything to the left of it. The problem is I don't know the standard deviation, so I have no context of knowing. Actually, it does. It says that she's at the 90th percentile, okay? All right, 90th percentile, which means what? Well, that means that her proportion is at 0.9, right? 0.90. So if you went to your chart on your z-score table, you would find in the middle where 0.90 corresponds to your z-score. Well, what is a z-score? Well, z-score, very important. Those of you who have this as your job, come on. Z-score is the amount of standard deviations from the mean. So you could have both a positive or a negative z-score. So what you'll do is you'll go into the middle. Actually, what I'm going to do, I'm going to pull up the formula sheet so you can kind of see this here. But you're going to go to the formula sheet. Make sure that you have that tomorrow. When you pull that up, and this one, you have to use this, okay? You have to go and let me. I want to show you why that's the case. I do need to do that just to show you why I would have to do that. But I'm going to answer this formula, and then afterwards, I think that will help us, okay? So we're trying to look for 0.90 on the interior, okay? Remember, we're talking about everything that's to the left of the line, okay? Because the 90th percentile means everything to the left of it's shaded. So we're going to kill this here. I just want to show this to you. And I'll show you the calculator part. Let's just show you why that's the case, okay? So 0.90 would be approximately probably right here. So the z-score of this means that we would have 1.28, okay? 1.28. So we're gonna take 1.28 there. Let's do this. 1.28. Okay, so we're gonna take this here. Okay, good. All right, so 1.28 would be my z-score. So just kind of hold on just for a second. If the z-score is 1.28, that means that we have approximately, we are 1.28 standard deviations from the mean. Now, as I go down, I remember that my z-score equals x minus x mean, right, divided by my standard deviation. The problem is I don't know my standard deviation, but that's okay. We could plug in what we know. So we would say 1.28 equals, what's my x? 40. What's my mean? 38. So 40 minus 38 is 2. Gotcha there. Divided by my standard deviation. So I'm going to multiply by my standard deviation both sides. Got some math going on. So 1.28 times my standard deviation equals 2. We're then going to divide by 1.28 to say then 2 divided by 1.28 equals 1.56. Or we could say, oh, actually, that's perfect. It actually would be 1.56, which is E. So this formula, big deal, just in case, because I can't go to my calculator. Remember, when I am trying to do, and this is kind of a key concept here, okay? When I am trying to do normal CDF, and then I plug in, and I'm going to show you where we go for that. Normal CDF would be when we are finding the percentile, when we are finding the area between two values. If I came to this one, and I'll show you in a second how I would do it. If I came and said 44, what percentile would 44 inches be? I could find that by going to normal CDF, okay? That's normal CDF. Let's hold on that, okay? The next one, inverse norm. Inverse norm is the second one. It's kind of the opposite of normal CDF, but inverse norm is when we are finding the value. Or I'm trying to think. Yeah, value's probably the best, right? So for this one, if I said what was the inches of children of height, right? What was the how tall would children be if they were in the 10th percentile, right? So let's do this. Let's actually do this here because I think this would be beneficial. I think. Let's go 10th percentile using this example. Okay. Get this out of here. And I'm going to do the 44 inches, okay? So I'm going to do this one, normal CDF. When we have 44 inches, what is the percentile? And when we are in the 10th percentile, what is it in terms of inches, okay? Now, the beauty of this is we can do this. Now, the problem with the one below, and you'll see why in a second, really, if we were going to use any one, we would use inverse norm. But let me show you why that I can't do that, okay? Now, take a snapshot of this just really quick because I'm going to pull up that calculator here. And that way I can show you kind of the ins and outs of this. And if I haven't gotten to your question yet, I'm sorry. I know there's a lot of questions out there. And so I'm going to keep trying to rock and roll as quickly as possible without rushing too much there. But if you went to stat and you went to calculate, oh, I'm sorry. This is different. Right over here, this is more like linear, like LSRL, least squared regression line of best fit. Over here with the VARS, when you go to second VARS over there, that's where the normal distribution stuff is, okay? So you're going to go to normal CDF, right? And this is where you put your lower, upper, mean, standard deviation, and all that, okay? But if you remembered the one we just did, if you go to inverse norm and you put in negative, I'm just going to put negative 10,000 or whatever, I don't know. And the next one, my upper was, if you remember, my upper would be 44, right? And then my mean was, no, hold up. What was it again? It was 38, my fault. 38 was my mean, and then this one was 40, I believe. Let me make sure. Yeah, so I'm just doing this problem. The problem with this is because I don't know my standard deviation here. That means I can't solve for this. So using the z-score formula and being familiar with that is also just as important as using your calculator, okay? Now let's come back to it. Let's actually look with that inverse norm or with the normal CDF here. Actually, I did do there. Let me go to the right one, the one that I was supposed to use, inverse norm. There we go. The area for our example, the 90th percentile, right? The mean was 38, right? And again, just like I said before, this is the standard deviation. Again, normally we're going to go left of it, so that way we can, again, we're shading left and going from there. But we know this is 1.56, I believe, or 1.56. And I said on the previous example, what if I took this, sorry, I'm going to do this here. It's not letting me get here. Let me do this one more time. Trying to get that calculator up. What if I found one in the 10th percentile, right? So what if I got 1.56, so 0.1, is the 10th percentile is 0.1, right? 1.56 is here. What would be the total height in inches of a child in the 10th percentile? And we're going left, perfect. Okay, it would be total inches would be 36.00 or 36 inches. Okay, perfect. So that's again how I go from percentile, the 0.1 or 10th percentile. Again, it's the left. That's how I would get here. Now, how would I get to it if I was saying what percentile is a child that's 44 inches? So again, here we're going to go second VARS. We're going to go to normal CDF. We're going to go to negative 1,000 because, again, this is way to the left, right? We want to go way to the left on that. My upper is 44. My mean, 38. My standard deviation, 1.56. We'll paste that, plug it in. Oh, no. I put something in there. Oh, yeah, that's my fault. Put a negative instead of or put a minus instead of a negative. So be sure to put that one. That's good. So negative 1,000. There we go. Once I plug that in, I should get on this one 0.9999. That's really, really large, right? So that would be like the 99.99 percentile. People all the time said that I was in the 99.99 percentile in height, and just stuff happens, Stuff happens there. All right. Very good. Let's keep going to some other questions. Wow, hit that one hard. Actually, let me do this. Let me go one more variability, or I'm sorry, normal distribution. Keep looking at my text too. So I'm saying stuff, but I'm also looking at y'all's text as well, making sure we're all good. By the way, as we go through some of these, if there are some that you're like little questions on or whatever, let me know, and we'll go through those as well. Let me check out, see if there's any questions on this side. Yeah, Matthew, good question. Tomorrow we only have one FRQ to do, and that one is at home. You will not have any FRQs in class. There will be 16 multiple choice. 15 will be graded out of 16. You could miss one and still get a 100. Dab it out, okay? So, yes, so that's possible. Oh, yeah, Jordan, on campus, if you go to chapter 5, bottom right of chapter 5, bottom right of chapter 5, and if you're still confused, shoot me a text and I'll show it at the end of this. The ones that I'm showing you right now are all related to that review sheet, so feel free to do that accordingly, okay? All righty. All right, this one, normal distribution, says the figure below shows a normal density curve, okay? The following gives the best estimates for the mean and standard deviation of this normal distribution. Remember, just a heads up, when we do a normal distribution or a normal curve, remember that a lot of times there's nothing that's actually normal. And what denotes normal? Remember, there's a couple things with that. First of which, remember the mean is what we measure for anything that's symmetric. And normal distribution is symmetric. It follows the empirical rule, which means it's 68% between one positive and negative standard deviation to the left and right of the mean, 68, and then the 95 is 2, and then 99.7 is 3. So just a heads up on that. Which of the following gives the best estimates for the mean and standard deviation of this normal distribution? Well, kind of have a good idea as I go downward here. I would say 225 would be sufficient on there, okay? So I would say 225 would be here, here, and here. I would cross off A and B if I were you. And then what I would be looking for is what is an approximate standard deviation that might be there. Well, if this is here, let's eliminate 1 here. This one, if this is 225, we would say 25, if that's a standard deviation, we would go to the right and to the left. And so it would be like literally this tight. It would be like right here and right here, right? That's really tight for 68% of the data. That's not really true. So I would say that, first of all, these are canceled, but then also this one's canceled, right? 275, if I have this as my mean, right? Because we symmetric, so approximately symmetric. 275 added to 225 would be out yonder, right? Way down yonder on the Chattahoochee. So that'd be way out there. That wouldn't be there. So the only one that makes even any remote sense here would be 225 with 50 here and 50 here. And we could see that's a pretty good estimate of my empirical rule, which is approximately 68% of the data falls within one positive and negative standard deviations, okay? Also remember too, I saw something about like something on there about a z-score. If I say, if you look at your test, I think I had one, but like 1.2 z-score, just knowing how to interpret that, knowing how to decipher with that. If I said find the area between these two z-scores, right? Let's say negative 0.0 or negative 0.7 and 1.2. This is 1.2 standard deviations from the mean. This is negative 0.7 standard deviations from the mean. Knowing how to do that's a big, big deal, okay? Big, big deal. So I would definitely take a look at that there, okay? All right. Keep going. Just throwing stuff out there. See if there's anything else that I'm seeing that I'm like, All right, just checking them out. Again, as you check them out, please throw some at me if you see any that you're like, man, that's a tough one or whatnot. But those normal distribution ones are ones that would be really good to look through. Again, basic things like a histogram, knowing how to interpret a histogram, that's important. I would look at stuff like that. Again, knowing how to find the area and the normal distribution between two different values. So if in the previous example, right, let me see if I've got, maybe I don't have it. Please have it, please have it. Yeah, right here. So in this one, let's say that I said, what percentage of children fall between 38 and 40, right? The normal CDF is where I would go because percentile is what I use here. And my low would be 38, my high would be 40 with a mean of 38 and my standard deviation of 1.56. So just again, another heads up on that, just to kind of look at or look over there. Oh yes, this too. Okay. Oh yeah. I think I have this one. Do I have this one? Yeah, this one. Okay. Oh yeah. Okay. A large set of 1.3. A large set of data scores has a mean of 60 and a standard deviation of 18. Okay. Now think about this. Got to really think. Okay. If I have my normal distribution, I'll get a different color. Okay. All right. We got our we got a standard mean of 60 right here, right? Standard deviation of 18. If each score is doubled, right? So think about it. If I have a mean here, right? Let's say the mean is 10. If every score is doubled, if I multiply every score, if we got, let's say, 10 out of 12 on the last quiz, and I say, okay, I'm going to multiply by 10 to fit this in the grade book, or multiply by 2 to fit this in the grade book. The 2, when I multiply by whatever it may be, in this case 2, that means the mean will also be multiplied as well. Got me? So here's what we could say. Measures of center, okay? Our center with our mean, okay? In this case, mean. When multiplied or added, got me? We will also add or multiply and add. So think about this. If each score is doubled and then 5 is subtracted, this is going to then be subtracted, right? So we double this and then we subtract 5. Multiplied by 2, we get 20. Subtracted by 5, we get 15, right? That would be my new measure of center, or my new mean, right? So in this case, we have 60. So if 60, we doubled the mean, we get 120. We then subtract 5 from 120 to get 115. So my new mean would be a value of 115, okay? So this also eliminates 3 of them, which is kind of nice, okay? So 115 would be my value. So mean is impacted by both multiplying and dividing and adding, and in this case, subtracting, okay? With standard deviation, think about this, okay? Let's go to the subtracting. Let's say the standard deviation, well, it's 18, right? The fact that I subtract this, if this subtracts by 5 and this subtracts by 5, aren't they, I want to show you this. Think about this. Here it is, right? We talk about our variability. Variability is the spreading out of data. Specifically, our variability we're measuring is standard deviation. So if our standard deviation is here and we subtract 5, that means I'm going to go to the left. Now, I hope this is to your left. I think it's still this way. So we're going to actually move to our left 5. So this one's moving 5 and this one's moving 5. Now, the center changed, right? Look, if I'm in the center, right? My Jordan's in the center right there. If we move 5, the measure of center changed, right? When I added or subtracted. But my measure of our standard deviation did not, right? Now watch this. What if I doubled this one? That doubled, let's say, was 10 to 20. And let's say this was 1. The fact that you multiply, they don't move together like when we add and subtract. They move at they move at different rates, right? So when we multiply or divide, we multiply and divide to get our standard deviation, and our standard deviation changes only when we multiply or divide, okay? Mean, you do it for multiply, divide, add, or subtract, okay? But just remember that visual. I think that will help you, okay? So if our standard deviation is 18, If we subtract 5, that does nothing to it. But if we double it, we double 18 to get 36. My answer should be B. Okay? Rockin'. Okay? Alrighty. Again, I'm just looking at a couple things. Let me go over some other topics y'all have brought up here. Sorry if I've thrown some off here. Gone a little off there. The FRQ is due Tuesday. Got me? Only one FRQ due Tuesday. Yeah, the one that says no extra, those are just extra problems. I just wanted to give you a ton of them in case you needed them. The one that says extra is the one that you do for tomorrow. Okay, let me say that again. The one that says extra, the one that I'm doing right here, is the ones you want to focus on, okay? The one FRQ, yes, it is due Tuesday. FRQ is due Tuesday, okay? Great question. All right. Let's see if we have any other questions here. Let me go to my Remind 101. Y'all are rocking, by the way. I appreciate y'all's help. Got some viewers out there. I'm hoping this is just as helpful as it possibly can be. 7 viewers in the house. Gotta love it. Rocking and rolling. Yeah, Tony, did that make sense? I think I went through all your stuff there, my man. Normal distribution, or at least as much as I remember teaching there. There could be something that I, for some reason, just didn't remember going over that if you need me to go over, I can. Yeah, so again, big deal. Adding or subtracting, the impact that has on standard deviation and mean. Big deal there. Z-score, big deal. That what I did earlier, big deal. Big deal. Big deal. I love the Phantom of the Opera. Anybody else love the Phantom of the Opera? Yeah, also, yes. Yes, good point right there. Yeah, okay. Variance, standard deviation, hit that. Just know that rule. Variance is standard deviation. Big deal. All right. Can you do a problem regarding normal distribution and or finding percent from, again, standard deviation to mean? Alyssa, I think I did that, but check me on that one. I think I already hit that, but I want to make sure that I did there. Okay. All right. Okay. What one? Someone just texted me. I'm going to miss this one. What one again? I'm sorry. I'm just looking at some different things that people are texting me in, trying to get. Right now, there's not a whole lot of things that people have texted in there. So we can look at some of those things there. I did normal distribution. I did residuals, numerical characteristic. Oh, yes. Good one. Yes. I actually want to pull this up. Like, I legit want to pull this up. All right, let me pull this one here. I'm pulling up, just in case you're like, Coach, what are you doing? I want to pull up 4.3. In 4.3, I want to specifically go over, let me see, I'm going here. Hold up, not that one. My fault, y'all. I think I did that one. I think I did 4.2, and so that's why I'm opening. I want to do 4.2, and the reason why I want to do that is I want to go to the last page. This part right here is very important, and I just want to make sure we just completely emphasize it because it really brings in a lot of the chapters 1 through 4 together. I think it was back here. I think I missed it. I think it keeps going, my fault. But it talks about a little bit, yeah, right back here. The last slide right here, the inference about population. If the individuals were randomly selected, then we can make inference about the population, okay? Please, on your FRQ and on the multiple choice, keep this in mind. So we think observational studies, right? Also, when we talk about correlation, we do not say cause and effect. Make sure of that. So I'm just talking about inference. Like when we infer something, we can say that something ... correlates to what? I'm sorry. I'm trying to write this by hand. Correlates to another ... right? But it's no causation or cause and effect. That's a huge thing. No cause and effect, no causation, okay? Sorry, I'm trying to write it. So observational studies infer about the population. For instance, if I have 100 individual, or let's say we have all of GAC, right? And let's say I took a simple random sample. By the way, if you need an explanation of simple random sample and you still don't understand, I think I explained it a lot better to the 7th period class today. Did some research, sought some advice from Miss Wilson, some other people that had taught it before, and they agreed it was very confusing. Come on in, and if you fix that completely and do a good job of it, I'll give you full credit back on that part of the test. Those corrections are due next week sometime, okay? But let's say I take a simple random sample of 100 individuals from GAC. Let's say I just do a simple random sample. In that example, I could say that depending upon those 100, if they were talking about the dress code or homecoming, how did it go? Did you like the dress-up days? The responses of the 100 could allow us to make inference about our population of GAC. Got me? It's, again, because it's an observational study. However, if I did an experiment where I decided that I was going to take 100 people, okay, we'll just say that there's 100 people in our population, and let's say that I randomly assign them to 2 treatments, right? Let's say the treatment 1 is a specific sleeping drug, right? And treatment 2 is like a placebo, right? It's a control group. And let's say after those treatments, they did their thing, right? You imposed the treatment, and then afterwards you compared, right? In this example, this would be an experimental design right here. And because of that, when we have an experiment, we can make an inference about what we call cause and effect, causation, right? Cause and effect. Now, the reason why I want to just emphasize this is because when you go to something either on an FRQ or on a multiple choice, just be careful in reading those appropriately and understanding that it's either a correlation or we can't say causation. Remember, the explanatory explains, or as something happens, it correlates to the response, right? And then when discussing the scope of inference, we always use context. So just a heads up on that. I know this is awful, but I probably could type this probably a lot better, but that would be what we would do there, okay? Awesome. Also in a correlation, let's go back to this one. If I added on this right here, let's say that, oh dang, in this correlation, we forgot to add 5 feet to this, okay? Man, dadgummit, I forgot to add 5 feet. Would that change our R? Would that change our R squared? The answer is no. Correlation of determination and our correlation coefficient, both of those are, those both have no effect if we multiply, add, divide, or subtract, right? R and R squared they don't care what is the X and what's the Y. All it does is say how closely are these related to each other, right? It's basically the gist of it. Now, what would happen to the R, the least squared regression line, the R squared, if I had an outlier out here? Well, because of this, what would happen is they would change, and that's something important to know, that R squared and R would change if we had an outlier that was on the outside of this. So based on, I think I messed this one up actually in the breakout room, and my apology for this as I look back on it. Or I just wrote it down wrong. I thought it was right, but I wrote the wrong one down. The reality is that these are not resistant to outliers. The outliers impacted there, okay? All right, so just be careful. Outliers do impact the R squared and least squared regression line there, okay? All righty. All right. I'm trying to keep going through some questions y'all have. I've hit a lot of them, a lot of questions that I've already hit there. We're on right now over an hour. Good gosh, we are good to go. Last question. Okay, good. We are good. We've hit a lot of stuff, y'all. Are there any other last minute questions that we can go over real quick? Appreciate y'all's time. I tried to give you a little bit of extra stuff today to really look at and go over. Feel free to, again, come in early tomorrow morning. We'll do those together. Make sure the FRQs are done by next Tuesday. And other than that, hey, I want y'all to know this, and I think you do, but I want y'all to know that, man, I just really do love this AP Stats class. I know I've asked a lot of you this week. I know it's an AP level class. There's a lot required of you, but it's because I want at the end of this semester, I'm trying to get you to get to a point where you can get that grade for that college. Nothing would make me more happy than with some of you that have really put the time and effort for us to really celebrate the effort that you put forth and do our very best on that AP exam. I appreciate y'all. I really do love y'all. Come home and tell my wife all the time, which is not every class and not every year. This year has been awesome within all my classes, and AP Stats has really been an awesome, awesome experience. I don't say it enough, but I do. I care about y'all. I love y'all. Let's dominate it tomorrow. Come in early. I'll be there tomorrow morning by 7 to 7:15. Even if you want to come later, hop on in. No pre-cal tomorrow morning. So just y'all, come on by. Let's get some help there and go from there. Obviously, I've got to do the shot. Here we go. Oh, just shy. Have a great day. See y'all. Bye.